Hello, I'm K. Batwell from Electronic Design. The following AI-aided engineering tutorial is so valuable. It's the perfect hello world for using AI to design a working sensor-based application. This tutorial essentially replicates a project that took me over a month to build, but this time it's done in under 40 minutes. It's shocking, to me at least. François from STMicroelectronics takes us through building this project from start to finish in this following succinct video. Bookmark and save this video for future reference. Enjoy.
Hello everyone, my name is François. I'm working at STMicroelectronics in south of France. And the idea of this video is to guiding you through the different steps to create a smart sensor device with embedded AI. And to do so, we are going to use STMicroelectronics free tools, and specifically ones that is named NanoEdge AI Studio. The final result will be a sensor that is able to monitor and to detect anomalies on industrial machineries. Could be useful for HVAC, for example, system pumps or any kind of electrical motors. And I will let you imagine the possibilities and other variation of the same idea by yourself, of course. So here on the side of my desk, I have this very rudimental setup that with two fans that are generating vibration. They are here to mimic some kind of machinery. We want to be able to monitor using our new smart sensor that we will create together. So I already prepared some kind of demonstrator, and I will show you here. So on this those board that came from Adafruit, so you can find them very easily. There is the first one is a development board with an STM32, and here you have a small OLED screen, and on the side I used an accelerometer, and of course there is a battery. So if we start this sensor by plugging the battery like this, okay. So you should see on the screen that, whoa! Okay, let's reset and retest that. Okay, I used only one magnet, it's not enough. So you can see on the screen here, we are entering a learning phase inside the microcontroller. So during that phase, basically the system, the main program, is collecting some data sets, vibration data set from the accelerometer, and sending those locally inside the main program to a dedicated AI library. This library is creating locally a model of the behavior of that machine. So the vibration from the two fans that are working alternatively. That's why the learning phase lasts long enough to go through the different possibilities, the different combination of vibration from the two fans. And after that, it switches automatically to inference mode. In that mode, every second, the system will collect a new batch of buffer of vibration from the accelerometer and will compare them to the model that has been created. And if we change the way the fans are running, we should go outside of a 100% similarity level. So if I switch that to this mode, you see the fans are running differently. And so on the screen you can read that the similarity level dropped to 0%, meaning that it no longer it's not any longer similar to what has been seen by the system during the training phase. And so we trigger an anomaly. We say on the screen there is something abnormal occurring on the machine. And from there you can imagine the rest of the journey where you can connect to a cloud system to trigger the alert, or you can trigger a different color of LED or a buzzer, whatever. I let you imagine the rest of the possibilities. So the idea is, how do we create that kind of sensor? Because if we are using the classical way of creating things, the classical way of programming things, it will be a little bit challenging. Why? Because if you want to determine which are the trigger in terms of vibration, that should trigger an alarm. And to say this is abnormal, it's a huge pain, because there is a lot of combination possible. So to find what does it mean something abnormal outside of the normal behavior of a system that sometimes you don't really know well. If you are designing a sensor, for example, for pumps, every pump could be different in terms of vibration. So it will be an infinite challenge to find the right threshold for your algorithm. That's why it makes sense to go through machine learning and AI approach to fix that issue, and we will see together how to create those small machine learning algorithms for microcontrollers. Okay, so enough from my crude demonstrator. Let's go to a more classical development board from ST. So here I have this Nucleo board, and the idea is that we will start by creating our data logger, because we need to collect some data. At that stage, the first thing you should do is to download and install NanoEdge AI Studio. So NanoEdge AI Studio, you will find it very easily on our website. So you have here the URL stm32ai.st.com, and here you just click on Product, NanoEdge AI Studio, and of course you can download NanoEdge AI Studio from there. Of course, I already installed NanoEdge AI Studio, so it's a desktop software. It's available on Windows and Ubuntu, and it's free to use in any way. So let's start the studio. It's here. On the main screen you will see different things. You get access to tutorials, of course, some inspiration use case in which Edge AI is meaningful to inspire you, and here you get your project. But first of all, we need a data logger to collect some data. So to do so, you can go to data logger, and here you will find, of course, you can create by yourself your own data logger, but if you don't want to do so, you can just go to the data logger area of the software and choose a board that is from the list that is currently available. So I choose this one in my case, and here you will find the different sensors that are existing on that board. In our case, we will use the vibration to monitor the machine. So let's pick the accelerometer, and then we can choose the different parameters of this accelerometer. So let's go for 256 values per axis. So it's a 3-axis accelerometer. The range, we can keep it at the maximum range, even if I'm pretty sure that we will not have that many vibration on a small scale like this. It's okay. And in terms of data rate, we can say, okay, 800 should be more than enough. Here you just click Generate Data Logger. It will compile a data logger for you, firmware. You will get the zip file with the firmware inside. Then you just have to go and drag and drop the firmware. You save it on your computer, and then you drag and drop on the board. It will flash the board in data logger mode. If you want to go a little bit further, what you can do is go and check our GitHub with the source code of this data logger, and we will use that source code to create our demonstrator after. So you just hit GitHub, the URL that is here, you get to the corresponding GitHub, you can download the source code, and you can compile from STM32 from Cube IDE the corresponding project to create simply your data logger from the source if you prefer to do so. So at that stage we have a data logger. So if we open a serial port, and so let's start PuTTY. So it should be on serial 12, I think, if I remember. And open, let's open. So here you can see on the screen, there are buffers of data that are flowing. Oh no, the data rate is not, the bit rate is not good. Let me try again. Sorry, putty, serial, COM12, the speed is higher. Okay, should be good this time. Okay, so you can see here on the screen the buffers of data that are flowing from the accelerometer to my computer. So now we will use those data sets, and those are corresponding to the vibration of the fans that are here. So now it's working well. Let's go and use those data sets in a project. So on the main screen of the studio, what we want to create together today is an anomaly detection solution. But using the studio, and we will go through other kind of project, you can create a one-class classifier, but you can also create a very classic classifier of events, of classes. But you can also do extrapolation, meaning regression. Let's go and create our anomaly detection tool library. Let's go. So name of the project, it's fine. Target selection. So here you will find basically any development board from ST, almost every. And in our case, we are using this one. It's in my favorites. But to show you, there is really plenty of them. So you can apply the same tutorial to a different board, of course. But you can also go targeting directly a specific microcontroller family. If you already have your development board that is not one from ST, you can set, okay, it's in my case, it's using STM32F4 something. So in reality, I just have to say, okay, it's this one, and confirm. So no, in this one it's not an F4, it's a L5, but you understood. Okay, so I'm using this board, this one, confirm. Now the sensor part of the project. In my case, it's a 3-axis accelerometer, but you can use different kind of signals for different kind of project. Could be a microphone, could be a current sensor, could be a Hall effect sensor, could be a combination of sensors if you prefer, or it could be whatever kind of signal. So you can set generic if it's another kind of sensor. In my case, I will say 3-axis accelerometer. Yes, this I set OK, confirm, and we are good to go. We don't know the limitation in terms of RAM. At that stage, 32 kilobytes is more than enough, I think, and we will not put any limits on flash, but in reality we will a lot below that 64 kilobytes, so it's good. Let's continue. So at that stage of the project, so you understand that we are following this path with number 1, 2, 3, 4, 5, 6, 7 steps to create this AI library we want to use in our project. The first step is to create, to give some example of regular signal, meaning when the machine is running well. In my example, I will say, okay, when the fans are in this green light, means it's running well. So I need to collect some data for that. I can import from files, but I want to show you how to collect live using the serial port. It's easier. So as you may remember, we set this board in data logging mode. So if I listen to the serial port and record those values, I will get, so let's start this, start. Okay, you will see on the screen here a representation of the vibration that are collected through the serial port to my computer, to the studio. You can see here an output. And we decided to collect 100 of them. Why 100? Because I think it will be enough to go through the different steps of the different combination of the fans that are running. If your project involves a lot more variety of signals, you should collect a fair amount of them to represent the usual behavior of the machine or the system you want to monitor. Let's continue, that's fine, and let's import. So here we have our 100 lines with those 128 values per axis, and you get per axis a preview of the content of the file, and with a Fourier transform, so we can see the frequency involved on different axes, and you can see on the last one that we see more than one frequency involved. That's because the two fans are not running at the same time. Okay, that's cool. Now, next step, provide some example of abnormal signal. As I said previously, we cannot predict any anomalies. So here, the idea is not to be exhaustive. It's more to be to present to the studio something that is realistic. So in my example, I will use my second pattern, running pattern on my fans as an anomaly. And I will collect those signals again from serial port 12, 100 lines, let's go. So you can already see that on the screen that the vibration is completely different. We have a lot of noise on the axis 3. That was not the case previously, I think. And if you have a different setup, and you will, of course, you have to find a way to create something that is realistic in terms of anomaly. Sometimes it could be a little bit challenging. So, for example, for a pump, you can close a little bit the pipe that is going to the pump. So you create some kind of effort from the pump. It will generate something that is realistic. It's good enough. You don't have to go through every anomalies, because this is impossible. We will let the microcontroller train itself locally on the device. This is specific to anomaly detection in NanoEdge AI Studio. I will explain to you later on. So here again we have a preview of the vibration, the signal on the different axes. That's fine. Now we will reach in my point of view, the most interesting part of the process. So here, usually at that stage, mathematics should be involved. You will have to, for machine learning and AI in general, you will have to create your model. You will have to use scripts and frameworks to create that. And this could be a little bit tedious, usually. But here it's completely different, because we will let the machine do the hard work for us. To do so, let's run a new benchmark. So here we are providing the regular and the abnormal signal we already logged previously. We just hit start. And here you will see on the screen that the tool locally on your computer using your CPU is going to go through different combination of algorithm to find the perfect combination for your project. So the project you describe using those signals. And by different algorithm, I mean there are fundamental bricks that are developed here by the team. And some are around signal processing. For example, you can have a fast Fourier transform. Some are around machine learning, and some are around feature extraction. And the system is going to combine them in a smart way to find which combination can solve the problem I show to the machine. So progressively, my computer is improving the solution. You can see here on this part of the screen that there has already been almost 200 libraries that has been tested by the system. We reached 200 now. And each time there is a new potential solution, the system will display the best score based on the balance accuracy, meaning the accuracy of the library, the capacity to distinguish between a normal signal and an anomaly. That is the goal of this library. So this is the most important aspect of it, but also the system will try to optimize the RAM consumption and of course the flash consumption. So here on the right side you can see on this graph the progress that occurred. So we started from a 50-50 balance accuracy, meaning you flip a coin, to something that is very good at 97%. On my PC, it's a simple laptop, in matter of 2 minutes. Okay, so you have to compare that. I'm not a data scientist, but without any effort, I was able to reach that point in terms of quality. Okay, so I think we are pretty okay with the result. So we will stop the benchmark here. In reality, you can let the benchmark run. Maybe there are better solutions ahead of us, but for the purpose of the demonstration, I think we are good enough. So let's stop the benchmark here. And let's continue the process. So the benchmark will show you the best result. Okay. And here you will get, in terms of information, the score, the balance accuracy, the amount of RAM and flash consumed by the library, but also you can see other possibilities, because sometimes you want to consume less RAM and flash for the purpose of your functionality, and you are ready to do a trade-off for that. So in my example, maybe I say, okay, I can lose 1% of score of accuracy if I divide my RAM by 3. Could make sense. So if you want to do so, you just selected that library, and you are good to go with that library. But I will keep the first one for this demo. So now what we can do is the validation steps. So here you can see that the system has already pre-calculated estimate the execution time that you will get if you run that library on a typical Cortex-M4 microcontroller. This is a good indication to compare libraries, the one with the other. It's completely software based, so it's an estimation, but could be very useful also if you want to prioritize real time, for example. And you can ask for the estimation for the different libraries that you are interested in, and you will get the result here. You can also compare the library with more data sets, because at that point of the project, we only collect 100 lines per signal, per phase, nominal and normal. If you want to confirm that the library is the best one between the one that are proposed by the system, I really encourage you to collect more data from the serial port, for example, and then to trigger an experiment, meaning a comparison between different libraries, that maybe the ones that are faster or the ones that are consuming less RAM, to confirm that the one you want to use is this one. Now, let's go to the emulator stage. Here the idea is to help you gain some time on testing purpose. So, of course, at that stage, we could install the library on the board and flash the board and do some testing, but it could be a little bit long. So we developed this emulator. The emulator is going to behave exactly the same way the library is going to behave on your microcontroller, but only running on your computer. So here the system will compile a version of the library for your computer, for Windows in my example, and we will run that library locally using some data from the serial port. So if I switch back my setup to green, nominal, what I can do is train my library for the same way I showed you with my small device at the beginning of this video. We will do the same using this accelerometer, the one that is on that board, with our new library that we created together. So I will ask for, let's say, 40 buffers to train, or maybe 60. Let's go 60 to be sure that we go through the different phase. And we are connected on the right port with the right baud rate. Let's start. So here you can see the signals are flowing, and here you can see the number that is increasing, meaning those signals has been learned by the local library the same way it will inside your microcontroller in the future, but on my computer. So we ask for 60. Perfect. Let's go to detection. So here we are at the second phase, in which we will compare the signal to say, the local model will say, is it nominal or not? Is it similar to nominal or not? So let's start. So each time a buffer came from the serial port, from the accelerometer, it's locally compared with the library. And the similarity level, so to the response from the function of the library, is displayed here on that part of the screen. So it's very, it seems perfectly fine. Everything is nominal because we are having here the same patterns that we train on. But if I switch this and go to the red pattern, we can see that the similarity drops. Why? Because the vibrations are completely different. So the local model confirmed that the similarity is completely wrong. If I switch back to green mode, we should go back to a higher similarity level. But also if I hit that, we can see that also the similarity can drop. So the anomalies are not only the red pattern. Any kind of anomaly should trigger, you can see on the screen, a drop in similarity level. Again, you cannot predict any kind of anomalies on the system. That's why we had this strategy of training on normal behavior and then trigger on any kind of anomalies that are outside the model. So it's very pragmatic in terms of anomaly detection approach, and it makes a lot of sense if you want to create smart IoT devices to monitor any kind of phenomenon on any kind of machineries at home or at work. Could work everywhere. So let's stop that, and we are good to go. Last step on the studio is the compilation of the library. So we will ask for, we will let the parameters the way they are good. Here we will provide, you will have a small hello world to explain to you how to use the library. It's very simple for any kind of embedded developers. You just have to link, of course, your library. You set the number of learning iteration. In my example, I use 50, I think, or 60. So it's that parameter here. And then you are collecting some data from your accelerometer. It's business as usual. And then the interesting part is around anomaly detection learn. So this is the first loop, or training loop, in which I call NanoEdge AI detection learn with my buffer of data from my accelerometer. So I go 60 times in that loop. And then after that loop, I go in an infinite one that will fill the buffer with new fresh data and send them to NanoEdge anomaly detection detect function, in which you input the buffer and you get the similarity level as a response from the library. So very straightforward. for any kind of embedded developer, I think. So let's hit compile library, get library. Let's say I'm a hobbyist. And the library will be downloaded on my computer. It's a zip file. Zip file download. So here I can extract the library. Okay, in the zip file you will find different things. You will find the emulator if you want to use the emulator on your computer as an executable file for Linux and Windows. But of course you will find the .a library and the .h file. So we will use that in our Cube ID project. So the project is here. To get the project, I used the source code from the data logger. You remember I said to you that you can, in that part of the studio, in data logger, here you get the source of the data logger. So I download the source, that is a Cube project, and then I open it here on my computer. In that file, you will find in the main .c, you will find some parameters you can adjust. You will find the sample size. You need to put the same value as you did on in your project. So if I take back my project, no, it's this one. So here my files were 120 values per axis. Okay, so I should set this value samples to the same value. You should not change that. Number of axis 3 in my example. The accelerometer, sensor type. Here you will also be able to set the frequencies values. So in my example, I think I use those ones, but you can change them also. If you need to find what are the possible values of the parameter, the accelerometer parameter, you can click here and say open declaration. You will get to the declaration file in which you can select the different frequencies of your accelerometer. And you can do the same with the number of the amplitude, the number of G's. And that's it, I think, for the accelerometer. Here you have two modes. So, and it's explained in the comments of the file. In mode 0, you are in data logger mode. So the mode we use to collect some data. If you switch to 1, you are entering the demo mode. So here, if we want to test our future device, we will go to demo mode. The number of learning, I said 60 in my test, so I will keep that value here. And the rest should be okay. So let's save those modifications. Now we should drag and drop or import the library we download from the studio. So the .a, the lib_nano.a go in this directory, copy file, overwrite, and this one, the .h, go to the source, the include category directory, sorry, copy file, overwrite. Now we will flash our board. Compilation. Building, okay. No drama. Waiting. Done. Cool. So let's open the serial port to check what is happening. Serial COM12. 14200. I should check also terminal. Yes. Okay, so let's reset the board to see the different steps. Okay, so you can see the learning is pretty fast, and you had on the screen. Can I do that? You can see the different learn steps from 1 to 60. Each time collecting a new buffer of data, and then automatically after that it switched to inference mode, monitoring mode. And you get the similarity level between what has been learned during that phase and what is occurring now. So we are 100% similar. If we switch to the other mode, you can see the similarity level drop to 0%. If we switch back to green, we are back to 100%. And if we hit that, you can create anomalies in the system and be able to detect them using our library. So we are good to go. At that point, I hope it was clear and easy to understand. At that point, the rest of the journey is for you guys, because we are entering really the embedded development part of it. Using that information, that similarity level, again, you can trigger a radio signal, an information you want to send back to a dashboard system. You can trigger some LEDs, some buzzers. The rest of the story is really for you, because here we are not anymore in the AI machine learning part of the project. It's a more classic part. But I really hope that you understand that anyone can use this NanoEdge AI software, this tool that is freely available for everyone, really, from our website. I will now show you a second kind of project using the same setup. Here we are going to do classification, because it's also a very classic usage of machine learning and AI to classify phenomena using signal from sensors. So let's do this. The idea is let's do a classifier that will be able to say, okay, is it green or red based only on vibration, okay? So it's an N-class classification with two classes. Let's create a new project. Again, I set my target to my wonderful board. This one. Confirm. I set my sensor to 3-axis accelerometer. I don't know why it doesn't keep my setup here. Save and next. Here it's slightly different from an anomaly detection project. As you can see, there is only a step 2. There is no 2 steps for signals, because here we will add 1 signal per class we want to be able to classify. So let's add a signal from serial USB, and here 100 should be again enough. Okay, no, I forgot to switch back to data logger. Okay, let's switch back to data logger. So I reopen my ID, and here I set NanoEdge AI mode from 1 to 0 to switch back to data logging mode. Okay. That's it. Okay, cool. If I reopen the studio, close. Close, yes. Let's add signal. Serial, start, stop, and here we go. So, the same as for anomaly detection, we use the signals from the serial port, from the accelerometer, same parameter. But the difference is that in that case, we will use them to create a classifier, not an anomaly detection solution. what we can do also is reuse the signal from the previous project. I will do this for the red signal. Okay. Almost done. Yes. Continue. Import. So we will name that green. Makes sense. Okay. And let's go to our anomaly detection project. Abnormal signal. We can export those. Download file. Save. Go back to our new project, and here we can add signal from file. Select file, download, select, continue, import. And this is the red pattern. Okay. So next step, so we have two classes, okay? We want to classify based on vibration in which pattern behavior the system is, green or red. The same way we run new benchmark, we want all classes, start, and again the system locally on your computer, on my computer, will train a model. Here it's slightly different compared to anomaly detection with onboard training because the knowledge will be static. We will create the knowledge, the model locally on the computer, not on the microcontroller, because those are finite. We want to classify phenomenon. We don't want to detect anomaly. So it's slightly different, but the benchmark is working the same way. So it starts from the challenge seems very easy to address in that example. So it already find a very good result. So now it's optimizing the amount of flash and RAM, and you can see on the screen that the amount of RAM and flash that is mandatory to run that libraries are very low. So that's pretty cool to have that. And in matter of 1 minute, it already tested almost 2,000 possible libraries and give us which one is the best without any effort from us and without talking any about algebra or mathematics in general. So let's stop here. We are more than good enough. And we will do the same. Okay, we can test this library using the emulator. So now I will compile an emulator for my computer. And we can test it using serial ports. So here we are in green phase, you can see on the screen. Let's go. And the library say, okay, yes, it's green. Based on vibration, it's green. If I switch to red, now it's classified as red. So the library is running very well. If I switch back to green, yes, now the results are green. So in matter of minutes, you can create those kind of simple but powerful classifier for your project. In that example, it doesn't make a lot of sense to have a classifier of those two, but I let you imagine what are the possibilities for your project. If you can create those AI machine learning based classifier that will run inside any microcontroller, any Cortex-M, any STM32 microcontroller, because it's not limited. It's a pure C code library, can run on any Cortex-M for all of your project. So I really encourage you to try by yourself. I think I try to give you the right amount of information for you to start. Don't be intimidated by AI, by machine learning and those buzzwords. We are embedded developers, and we create that tool for you, yes, and so everyone can use it. Thank you very much for your attention. If you have any question, you feel free to contact us on our website. And I really hope that you will create a very interesting project using our tool. Thank you.